Alright, hi guys. Today I'll be going over exponential versus linear functions. Okay. So, what is a linear function? Well, a linear function is a mathematical function in which the variables appear only in the first degree, so that's pretty important, and are multiplied by constants. So, constants could look something like this. So, imagine 2x, right? This is the variable, this is the constant. So, the variables appear only in the first degree, so like it would be like 2x to the first, right? That would be what it is. And then the constant would be the 2 in this scenario, okay? And are combined only by addition and subtraction, right? So it could be like 2x plus 1. So this is like what a linear function generally would look like, okay? I'll go over that more, though, in the further future slides. So what is an exponential function? Well, an exponential function is a mathematical function, and it is used to calculate the exponential growth or decay of a given set of data, okay? So that's important, the exponential growth or decay. And we'll be going over this. All right, so what does a linear function look like, okay? Well, a linear function is typically in the form y equals mx plus b. And not typically, it's always in the form y equals mx plus b, right? And what does this mean? Well, okay, let me actually break it up into some different parts, okay? So the m here represents the slope, okay? The b is the y-intercept. So this is used for slope, right? You could find your slope. So let's say I have a line, right? And let's say my slope is 2x, and then let's say my y-intercept is 1, like I had in the definition above, right? So let's say this is my linear equation, right? If I put it into this form, y equals 2x plus b, so you start with 1, right? So where is 0, comma 1? Let's just say 0, comma 1's right here. That's my y-intercept, okay? That's one of my points. And then, so how you interpret the slope is you interpret it by doing rise over run. So that's like the change in y over change in x, or the rise over the run, okay? That's how you interpret the slope. So in this case, it would be you rise 2, run 1, okay? So let's just say I'm just going to create a rough sketch of this. I'm not going to actually like put intervals and tick marks representing anything. So 2, 1, let's just say it's like 2, 1 here. So we're just going up by 2, and we're running 1. And what running means going in the next direction, 1. So it would just, in general, it would be a line that looks like this. I'm not going to actually like draw it completely. And it would actually go this way too, into the second and third quadrants. It would never go into the fourth quadrant because that's just the nature of this particular slope. And again, like I said, it could go negative too. So you could have a negative slope, which is the same idea. It's still rise over run, and the y-intercept is still b. Okay, so that's just kind of how you decipher that. So what does an exponential function look like? So y equals a times b to the power of x. All right, so a is the initial value, okay? B is the rate, okay? It's the rate in which you are increasing. So sometimes it's like 0.85. Sometimes it's greater than 1, so it'd be like 1.5, okay? And then to the power of x, right? So what would this look like, right? What would this look like? Generally, exponential function questions would go like this, something like this. Like the most arbitrary kind of like vague graph that you will see about an exponential function will look something like this, where it just, as x is increasing, y increases more rapidly. So sometimes you'll have something where it doubles every interval of x. And that the formula for when it doubles is y equals a, whatever the initial value is, 2 to the x. And obviously you know it doubles because there's a 2 for the rate, right? And there's also halftime, which we'll go over in another video. Halftime means it's literally y equals a times 1/2 to the x. So this is the rate. That's what halftime means. And we'll go over that. That's a little more difficult for exponential functions, but we'll go over that later. And again, I already showed you examples of linear function graphs, but I'll show you more examples, right? The more the better. So here we have a linear function graph that I just pulled from Google, and let's interpret the equation for the line here. So we obviously have 2 points, and this is the xy plane, so we see that it's 3 and then -2. So 3 is the x value, -2 is the y, and then here we see that it's 0 and then -4, okay? So 0 is the x value, -4 is the y. And I don't know if I went over this, but I'll go over it now. You could find a slope of a line, the m in the y equals mx plus b, by simply having 2 coordinate points. In this case, I have 2 coordinate points, 3, -2, and 0, -4, so I'll use that to find the slope. And like I said, the slope is change in y over change in x. So if you were to do this, you could make this x2, y2, and this will be my x1, y1 coordinates, right? So I could do change in y over change in x is just the simple formula for that is y2 minus y1. So if you have 2 points, y2 minus y1, x2 minus x1, okay? That's the change in y over change in x. So what's my y2? I'll just plug it in, -2. As you can see, y2, -2. What's my y1? -4. So minus -4. Don't just do -4. That's not the same thing. What's my x2? My x2 is 3. And what's my x1? My x1 is 0. So now I would actually get the slope. So -2 minus -4 is the same thing as -2 minus is plus 4. -2 plus 4, what is that? It's 2. All right, and then 3 minus 0 is 3. So this is our slope. This is our m value. So now we can make this 2/3 x plus whatever our y-intercept is. And in this case, it's fairly easy because we actually use the y-intercept as one of our points that we in our slope-intercept form. So we used our y-intercept as one of them. And our y-intercept just means whenever x is 0, what is the value of y? In this case, when x is 0, y equals -4. So plus -4, and this right here is our equation of this linear function graph. All right, so now we'll go over the exponential function graph, right? This is just in general, this is just in general what it looks like. So as you can see, as our x values are increasing, this is arrow just indicates that x is increasing, right? Our y values over smaller intervals is increasing more rapidly, right? So obviously in the beginning, when we're looking at this part here, the slope is like, it's like nothing. The slope is like nothing, okay? It's like 1 maybe. But then as you get higher, and this is like the defining feature of a exponential function graph. As you get higher, you could see the slope, which is just the rise over run. So rise, run, is so much higher than here. Look at the rise over run here. It's like 1/5. And then here it's like 5/2, 5/3. This is without any, I'm not actually doing the math here, but I'm just saying you could see it's way steeper on the latter end of the exponential function. And it's just going to keep on, it's just going to keep on going up. It's going to keep going up exponentially. Okay? So this is just in general what an exponential graph is. All the key concept for exponential functions is that as x increases, y will increase more rapidly, right? It'll increase more rapidly as x increases. So in a smaller interval too. That's the key concept. All right, so here are some input values for x on the left column here. Then we have 2 to the x, which is an exponential function. And then 2 times the x is linear, so I'll actually label this linear here, exponential here. And this thing is just our input, okay? So obviously, all you really have to do, there's nothing special about it. You just input the values of x into our exponential like 2 to the power of x right there. So what is 2 to the power of 0? Because x is 0. 1. 2 to the power of 1, 2. 2 to the power of 2, 4. 2 to the power of 3, 8. 2 to the power of 4, 16. You could see it's doubling, right? 1 to 2 times 2. 2 to 4 times 2. This is not always the case, but in this case, it is doubling because, as you can see, the rate of change is 2. What did I say? It's doubling. And like in the example above, remember in the definition I said, one example would be like y equals a times 2 to the power of x, right? And in that one, it's doubling too. Here, the default value for a, when we're not given any value of a, is just 1. So this is the same thing as y equals a times 2 to the x. Okay, this is pretty much the same thing as this. Okay. So that's just the kind of the pattern here, times 2 times 2. And then the graph, like I said, it would be increasing exponentially. The graph would look something like this. It would like skyrocket. Not necessarily, but it would go like that. Right? And slowly the slope will just get bigger and bigger every time. Okay. And not the slope. You know what I'm saying? 2 times x is linear, right? This one just, you could assume that the y-intercept here is just 0, right? Even though it doesn't have it. So this is still following the same linear equation form. It just doesn't have a y-intercept for the sake of like inputting these values in. So 0 times 2 is 0, right? 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times... So you can see a common change of 2 between each of these values, right? And that's kind of how linear equations just work in general, right? You always see a common change rate, common rate. So in this case, you'll see something that's very true of linear equations. They will always be constant, right? So 2x, right? Y equals 2x plus 0. So this is 0 is our origin. That's our y-intercept as well. And then it'll just go up like this. It'll be a straight line. It'll be constant. It'll go up by 2 over 1 every time. Rise over run 2 over 1. Let's just say that's 2. That's 1. Okay. It's gonna go up like that every time. 2 over 1. 2 over 1. 2 over 1. 2 over 1. Like that. All right. So let's go over some examples. A ball is launched into the air. The linear equation above models the trajectory of the ball. What is the slope of this instance? What is the value of y after the ball has been in the air for 5 seconds? And assume that gravity just doesn't exist because the ball is just going to... you'll see later, but the ball will just keep on going up in this case. So what is the slope of this instance? Well, what did I say? Y equals mx plus b. The slope is always the m. In this case, m is equal to 3. So the slope we'll put as 3. What is the value of y after the ball has been launched in the air for 5 seconds? So all we do here is we know time is our x-axis, right? So that's our x values. For if it has been launched in the air for 5 seconds, we could just plug in 5 for x. And obviously we assume gravity doesn't exist, so it would be y equals 17. Probably feet, they never told us, but I would assume feet. Whatever unit they tell you, you should obviously indicate in your answer. And then this is an example of an exponential function. India's population was 1.25 billion people in 2013, with an annual growth rate of 1.2%. This situation is modeled by the growth function p of t equals 1.25, initial value 1.012, and this just is basically saying that our rate, right? So 1 plus, it's saying 1.2% growth rate. 1.2% is 0.012. Because 1.2 out of 100 is 0. Yeah, you get it. So it's 1.012 inside the rate here. Okay? And then to the power of t, 1.25 times 1.2012 to the power of t, where t is the number of years since 2013 to the nearest thousandth. What would be the population of India in 2031? all we really have to do is 2031 minus 2013 because that's the number of years. So we needed to get t in the first place. So 2031 minus 2013 is 11, 3, 20, 28, I think. I'm wrong? No. I'm wrong. It's 18. Okay, sorry. Sorry about that. 18 years since 2013. Where t is the number to the nearest thousand, what will be the population? All right, 2031. So all we have to do is plug in 13 now into our exponential function. So 1.25 times 1.012 to the power of t is 13 because we got in 2031, 18. Oh man, it'll be 18 because we got in 2031, it'll be 18 years since 2013. All we do is plug it in here. 1.25 times 1.0112 times the power of 18. I'll actually go to Desmos here, and I'll plug it in. Plug it in Desmos so I can actually show you guys. 1.25, 1.012 to the power of 13. And we would get the population, or POT, would be approximately 1.459, if we want to keep on going, 4.5, we'll just end off there, 1.4597 billion people compared to the number that we started, which like, 1.25 billion, so it did increase, and it increased exponentially as well. So, I hope you guys got something useful from this video. If you have any further questions, right, I would recommend checking out Lumen Learning and Khan Academy. They provide, Lumen Learning has a good article on this, and on Khan Academy in general, you could find most of these concepts on Khan Academy, just like Algebra 1 probably, right? So I would definitely recommend going there if you have any more questions. So that's my little verbal shout out. But also, these questions show up on, again, standardized tests, so they are pretty important. Even though they might seem a little easy as concepts, they will be pretty prevalent, so it's important to understand the fundamentals of them and just how they work. So I hope you guys will be able to identify these questions and actually know how to solve them after this. Not solve them, but how to graph them and how to interpret an equation from a graph. So I hope those are some things that you got out of this video, and thanks for watching.